Okay, so I just want to talk to you about the math for an oscillator. So what is an oscillator? Well, here is a little apple, and if I just pull it to one side, then it goes back and forth, back and forth, back and forth. And so we want to understand the position and velocity of this apple. And so that's what we're going to be doing in this little lesson here. So if you want an oscillating position, then you want a function that oscillates. So if you've ever looked at the graph of, say, sine of x or sine of time, then you get something that looks like this, like an oscillation. And here there are some unknown constants, a and b. And the first thing that you should know is, what are the SI units for a and b? Well, here I'm writing the position as a times sine of bt. So if we want position, then we know that on the left-hand side we're going to want meters. So on the right we need meters, but sine puts out something with no units. So to get meters, a has to have units of meters. And so what about b though? So sine also takes in something with no units. So whatever is inside of the sine can't have units. And since we know time has seconds, then b has to have 1 over seconds. So that's the units of b. Okay, so if you've done calculus before, then that's all of this, this activity that you probably need to know, because the point of the rest of this is going to be deriving what v of x as a function of time is. So basically, if you haven't done calculus, it's no problem. This class doesn't involve calculus, but it's basically taking the derivative of this to get what the velocity is. So instead, what we'll do, if you haven't calculus, then we'll just be looking at slopes to figure out what the velocity is. So let's consider that you have the position is just 1, so this is 1 meter. This is our a equals 1 here, and our b equals 1. This is 1 with the units of 1 over seconds. And so what that looks like on a graph where this is our x, and we have time going along this direction, so time going along here, this is what this sine of t is going to look like. It sort of goes up and down, and that's like the back and forth of the apple, basically saying that, okay, so we have our x going this way, x going that way. That's up and down, up and down. But don't worry about the height of this with reference to this line, because we're using this line to denote the position of the velocity. So how fast is the velocity going from this line here? I'll explain what I mean. So right here, this is the x graph, and if we look at the slope of this, we know that the slope of the x will give us the velocity in the x direction. So what would you guess the slope is right around here? Well, it looks to me like it's maybe 1 or 2. It looks like 1 to me. Let's just say that it's, we know it's positive. How about that? That's the important part. And then if we look at it right here, what's the slope there? Well, it's flat straight across, and so we know the slope. So I'm just writing what is the velocity going to be, positive, negative, or 0. And so I'm just taking the position going down to velocity. So here, since the slope is 0, we have velocity 0 there. Here we have a slope that's negative, so bringing that down, we have a negative slope, 0 slope here. Okay, and you get the idea. You could keep going all day. And let me just go on just a little more so you see what this ends up looking like. Here again at 0. And so you see that you're getting something that's looking like this. And if you're familiar with your sine, cosine functions, what you'll realize is that this function is actually cosine of t. So that's the form of it. Now, so we know a little bit about what the velocity is if we have our position as sine. It looks like a cosine. But what if we don't have 1 for a and b? How does the velocity change? So here we have a equals 1, here we have a equals 2, and here we have a equals 3. And then this is our position graph for each of these. And now what we want to do is we want to figure out what would our Vx be for each of these. Well, let's look at the slope here. So if this is, so let's assume that this one was 1 times cosine of t. So again, what we have the same thing right here. So this is 1 times cosine of t. But now if we instead have a in our position equation as 2, we have the position plot going a little bit higher. So what that means is that the slope here is different. And it's actually different by a factor of 2. So here we're going to have, as a changes in the position graph, we're also going to have the velocity changing. So we'll have 2 cosine of t. And b doesn't change just because the frequency here is the same. So whatever is inside with the t is going to determine our frequency. And then here we have, it gets even higher, so our slope here is even slopier, which means our velocity in the x direction is going to be 3 cosine of t. Now I should say, if you're not following some of this, it's fine. I mean, you can always replay it, but what we're trying to get to is the final equation for what the velocity as a function of time will be if we know that the position is a sine of bt. So as long as you understand the final result, that's the important thing. So let's just go on and think about what happens if we change b. So here we have b equals 1, b equals 2, and b equals 3. And when you change b, you're changing the frequency. So b is in units of 1 over seconds, right? So that's a frequency. And that's in the unit, that's also called hertz. That's the unit for 1 over seconds. And if you notice here, how does the slope change as we change the b? Well, it looks like here again we have our same equation. So again, this is cosine of t. But as this gets squished, the x plot gets squished, we get v, and so these are all vx. Vx is going to be slopier because it got squished, so this is going to be 2 cosine of, and the frequency has also changed for this one, so we still have our 2 that was in the sine here. So the slope has changed, that's why we have the 2 here, and also the frequency, how quickly it's going up and down, is going to change here too. So the way that you could see that is if you did another plot like this, just looking at the slopes and figured out how quickly is the velocity going to go up and down, well, it'll track along with the x. So as the x gets squished, the velocity will get squished too. And then here, we're getting even slopier, and we're getting a frequency that is going even faster. So this is going to be 3 cosine of 3t. All right, so what that means is that if you have your a here in the front of sine, then that's going to be brought in front of your cosine. And if you have a b inside the sine, then when you go to your cosine for the velocity, then it's also brought out there. So what is the velocity for a function that's a sine of bx? It's going to be a times b times cosine of bt. And so this is the important result, and that's really all you'll need to know from this sheet, but I just wanted to show you how one can get that by looking at the slopes. I hope that's helpful.